Hello, I'm Mrs. Spellman. Welcome to GCSE Computer Science, topic 1.1.2. Let's get started. So this topic is in systems architecture. And you might want to pause the video to have a look at what we will be learning and see if there's any gaps in your knowledge or if you've got some prior understanding of this topic. Please fill out the ticket in your green book and we can move on. We know already that the purpose of the CPU is to carry out the fetch, decode, execute cycle, and it does this over and over again. What we're adding to that in this lesson is that it is doing that to the beat of a clock which is internal to the CPU. So the speed of that clock will affect its performance. Cache size, or cache, is also inside the CPU, and that affects performance. And a central processing unit can have more than one core, and that will affect its performance too. So we're going to look at these three, I call them C's: clock speed, cache, cores, and we're going to look at them in turn. You might want to pause the video now and think about speed and how you would define it. Have you got a formula? You might want to go online and look that up. So there's a nice link to maths, and my definition is speed is equal to distance over time. So the amount an object will travel in a given amount of time. So a Lamborghini can do over 300 kilometers. I don't find that very impressive because my car can do over 300 kilometers. So let's change that a little. A Lamborghini can do over 300 kilometers per hour. And now that is impressive because I really don't think my car can do that. So clock speed, how will that be measured? If a car is measured in kilometers per hour, how do we measure the clock inside the CPU? It's not actually traveling miles or kilometers, but what it is doing is it's carrying out cycles of the fetch, decode, execute cycle. It's measured in Hertz, and I'm giving you an example here of 1 gigahertz. A CPU with a clock speed of 1 gigahertz will actually be doing 1 billion cycles per second. And it's important we have that per second, just like we had the per hour on the speed of the Lamborghini. So I've got two computers here. Everything is equal except the speed of the clock. And also they are running the same algorithm, the same program. So the one with a higher clock speed will be faster. The one with a lower clock speed will be slower. And they are carrying out a particular set of instructions, and the one with the 4 gigahertz can do more instructions per second. So what have we learned about clock speed? We've learned today that the fetch execute cycle runs to the beat of an internal clock. The faster the clock, the more cycles can be executed per second. And this speed is measured in Hertz. So now let's move on to cache size. So you are familiar with the CPU, and cache is inside the CPU, and it has the data instructions needed immediately. RAM is new to you today. It's a random access memory, and that contains the current data and instructions. So the operating system manages memory, and what it tries to do is get this data and instructions needed immediately into cache. So the control unit, it needs to read from memory when it's carrying out the fetch, decode, execute cycle. It will head first to the cache, and if it gets a successful hit in cache, well then it doesn't need to get the data and instructions fetched from memory, so it will be quicker. So if we had a larger amount of cache, well then we could fit more data and instructions in here, and the control unit would be more successful in its hit rate. So that is why a larger cache size will improve the performance of the CPU. So once again, I have two computers. They're exactly the same. This time, their cache size is different. So the 14 megabyte of cache is larger than 10 megabyte, and therefore, if they're running the same algorithm, the same program, the one with the larger cache, the 14 megabytes, will perform faster. And that's it for cache. So what did we learn about cache size? We learned that cache is very close to the core of the CPU, and we learned that the control unit looks in cache first when it needs to read from memory. If the data instruction is in cache, then it does not need to look in RAM, which is further away and slower. A bigger cache will hold more, so the control unit will have a higher success rate of finding what it needs in cache. Finish cache, and now we're looking at the final C, which is cores. So we're thinking about multi-core architectures. So far we've been looking at a single core. A dual core just means that the processor will have two internal cores, and it will be able to share instructions and share the workload between those two cores. And for a quad core, that's 4 cores. So we need to think, would a dual core computer be twice as fast as a single core? And it's very unlikely. First of all, the algorithm needs to be suited to instructions to be run in parallel. So we'll be looking at that in a minute. But also there is an element of like organizing. The processor needs to organize the work between the two cores, and that's an overhead. So it's unlikely that it would be twice as fast. But we will see that sometimes it will definitely be faster. Once again, a link to maths, and I'd like you to pause the video and have a go at working out the area of this irregular shape. Now, I would like you to do that without the use of a calculator, because in our computer science exams, you will not be able to use a calculator. Okay, so I've done just that, and I have worked out first the area of rectangle A to be 40 centimeters squared. I've worked out the area of rectangle B to be 30 centimeters squared, and my final answer is 70 centimeters squared. Did you get that, and did you remember the squared for your units? Okay, if you did get that, you might have done rectangle B first and then rectangle A. But you wouldn't have, like me, you can't do both together. But if we have a computer attempting a problem like this, and it's got more than one core, it's a really good example of where one core could have worked out the area for A, the other could have worked out the area for B, and once both of them are finished, the overall area could be worked out. So an example of a problem that won't necessarily run twice as fast on a dual core, but it'll definitely run faster because it can take advantage of having more than one core. Another link to mathematics, and this is the Fibonacci sequence. I wonder if you've heard about it. I'm sure you have. If you haven't, why not pause the video and go online and find out about it? It's fascinating. Natural patterns occurring in nature, and they're beautiful. And here is one such example. And what we're looking at is the numerical sequence that goes with this. So starting at 0 and 1, I am adding these two numbers together, and that gives me 1. Now I'm looking at the last two numbers in the sequence, I'm adding them together, and I get 2. Again, I will look at the last two numbers in sequence, 1 and 2 gives me 3. And then 2 and 3 will give me 5, and 3 and 5 will give me 8. Now, if you had more than one core to attempt a problem like this, you wouldn't be able to take the task apart and give it to the two different cores. So let's say a program needs to output the first 20 numbers in the Fibonacci sequence. Well, that can't be broken down into parts. Each number in the sequence has to be worked out and can only be worked out until the number beforehand has been worked out. So having an extra core here is actually not going to help at all. Now I've got two computers that are exactly the same, but one is single core and the other is quad core. If they have the same algorithm to attempt, will the quad core be faster? Well, we have to say, can the instructions be carried out at the same time for the algorithm that we were running? So if that was the irregular shape, well, yes, of course, part of that algorithm can be run in parallel. It's what we call parallelizable. So then the quad core would be faster, not necessarily 4 times as fast, but it would be faster. If, on the other hand, the algorithm was print the first 20 numbers of Fibonacci sequence, well, it's no help to this computer here that has got 4 cores because it can't take advantage of them. The task can't be broken down and done in parallel. So therefore, in that example, the number of cores does not mean the computer will be faster. So they both will perform at the same speed for the Fibonacci sequence style algorithm. So what have we learned? We've learned that a multi-core processor may be able to perform faster than a single-core processor. We're going to see if the algorithm allows for instructions to be carried out in parallel. And we've also learned that dual core does not mean twice as fast. You might want to pause the video and have a look at the topics that we have covered. I hope that you have enjoyed this video, and if there's anything that you're unsure about, please just pop back to that part of the video. Don't forget to fill out your ticket and put the date on in your book. And that's it for now.